Throughout history, humans have developed and discovered various number systems that help them to describe the world around them. For instance, the first types of numbers that were created were the natural numbers, or in other words, the counting numbers, 1, 2, 3, 4, and so on. And those were good for being able to calculate and quantify whatever it is that early humans were counting. But over time, the numbers 0, negative numbers, fractions, decimals, square roots, pi, all of these numbers became important over history. But now there's a new type of number that was not looked upon as something important probably until about the 16th century, when we finally started to say, you know what, let's start looking at these numbers. And these numbers are referred to as the complex numbers. Let's start with this real number line. Okay, the real number line involves all of the numbers that we can actually find and get as solutions to equations. Okay, these are quantifiable. We can actually find these values and construct these, for instance, lengths of sides of a triangle. So what we've drawn here are all of the natural numbers and so on, 5, 6, 7, and so on. But then at one point, 0 was discovered as being the absence of quantity, the boundary between the positive and negative numbers, which means that there were also negative numbers, which we should realize are real results. They're the real number that's needed in order to add to the corresponding positive number to get to 0. So for instance, in order to apply the inverse property, we'd have to realize that 4 needs to add to -4 so that the result becomes 0. But then these aren't the only numbers. At some point in history, fractions became important. 1/2, for instance. Okay. 8/3, or rather 11/3, which is somewhere in between 3 and 4. 1.3 can actually be written as a fraction, 1 3/10 or 13/10. We could also say -2 1/3. So all these negative fractions, and these are what we consider our rational numbers. So we started with our natural numbers, all the black numbers here. Then we ended up adding our, and I guess I could refer to 0 as an integer as well. So now we see all of our whole numbers, positive, negative, and 0, become our integers. Then we have all of our rational numbers. So all of these numbers, even 2 is a rational number because it can be written as 2/1 or -3/1. So far we see all of these numbers, the innermost being the natural numbers. But all of the natural numbers here are enclosed in the set of all the integers. So if you take all of the positive whole numbers to be the natural numbers and add the negatives and 0, you now get the integers. But if you take all of those integers and now include all the other fractions of integers, those are considered the rational numbers. But then we have some numbers that we started to deal with, especially more in trigonometry. For instance, the square root of 2, or the square root of 7, or the negative square root of 12, or pi, or pi/2. So notice that all of these numbers are not rational because they can't be listed as ratios of integers. So we refer to those as the irrational numbers. The irrational numbers. Now those irrational numbers are separate from the rational numbers, okay, because these are opposites, right? They're rational and irrational are opposites. But if you take a look at all of these numbers together, notice that every single one of them was able to be placed in between other values on the real number line. So these are all real numbers because they exist. And I'm going to put those in quotes. They exist in quotes. But then we've got a whole other set of numbers, which we refer to as imaginary numbers, which is a really poor choice of term for whoever came up with this, because that implies that these don't exist and they're not important. Turns out, though, that they are actually very important, and we use them throughout history. They weren't important for quite a while, and a lot of times people just disregarded them and said there was no solution. But let's say we wanted to solve this equation, x squared plus 1 equals 0. And we'd like to find all the values of x that make that equation true. So what we can do first is we can subtract 1, and now we're told that x squared is equal to negative 1. Now, if x squared is equal to negative 1, then that means something very interesting here. It means that if I multiply some number by itself, the answer will be negative 1, which you can understand throughout much of history was ridiculous. Because if I multiply a positive number times a positive number, or I multiply a negative number times itself, regardless, that's going to equal a positive number. So how could it possibly ever equal negative 1? And so until the 16th century, people just disregarded this. And it wasn't even until the early 1900s that a man named Gaston Julia said, you know what, I understand that these are peculiar numbers, but why don't we go ahead and keep working with them and see if something interesting occurs? And sure enough, it does. Because if I end up taking, or going back a couple steps here and taking the square root of both sides, then that means that my solution is x equals the square root of negative 1, which mathematicians have now given the value of I. So there are, in fact, I should be careful with this as well, because when I solve this equation, since I took the square root, there's technically two answers, plus or minus the square root of I. So what that implies is that we now have these imaginary numbers where I is equal to the square root of negative 1. So this is just one imaginary number. There are an infinite amount of imaginary numbers, but the number I is referred to as the square root of negative 1. So now when I look at all of my imaginary numbers could be I, or 2I, or the negative square root of 3 times I. There's lots and lots of different ways to end up seeing imaginary numbers. But if I combine all of these numbers together, all of the real numbers, let's try not to do that. If I combine all of the real numbers plus all of the imaginary numbers, then I get the list of what we refer to as complex numbers. So it turns out that every number that's on this number line is a complex number, but we try to be more specific when we describe the type of number. For instance, I could say that pi is a complex number, but it would be better for me to say it's irrational. I could say that negative 1 is a complex number, but it would be better for me to say it's an integer. I could say that 1/2 is a complex number, but it would be better for me to say that it's rational. But the complex numbers are referred to as the sum of all real numbers plus imaginary numbers. So it's all the reals plus all of the imaginary, And since we know that all real numbers don't have an I, but all imaginary numbers do have an I, then the general form for all of these numbers is A plus BI. So for instance, if we wanted to look at a few different types of complex numbers, we might have 2 plus 3i, or negative root 5 minus 7i. So notice there's a difference between real numbers, imaginary numbers, and the complex numbers. And so this lesson is about being able to apply operations to complex numbers to see some interesting results. When looking at these examples, we should realize that all of these are taking the square roots of negative numbers, which implies that imaginary numbers will be involved in some form or another. So the first thing to recognize here is that this becomes the square root of negative 1 times 16. So since this is a product of two values, I can say the square root of negative 1 times the square root of 16. Well, we now know that the square root of negative 1, by definition, is the number I, while the square root of 16 is 4. So we know that the square root of negative 16 is 4i. So you can see that the easy way to simplify square roots of negative numbers is just to take the square root as normal and tack on an I because you know that it's a square root of a negative. So let's take a look at the square root of negative 48. Same idea here. We could rewrite this as the square root of negative 1 times the square root of 48. So we already know that if we take out an I could rewrite this as I times the square root of 48. And now I just have to simplify the square root of 48. Well, if we break that down by finding some perfect squares, we get 4 times 12. But notice that 12 is 4 times 3, so there's another 4 times 3. And now we can take the square root of each one of these. The square root of 4 gives 2. The square root of 4 gives another 2. And so all that's left inside is a 3. So notice that this now becomes 4i times the square root of 3. Now notice that this is, and maybe I should rewrite this as well, as saying I times 4 root 3. But the way we typically write this is by writing the imaginary number in front of the radical. And there's a really important reason as to why we do that instead of writing it after the number like we did over here. And that's because if I were to, perhaps I'm writing a bit messy, and I write 4 root 3 and I put the I out here, or maybe I don't write that messy and I put the square root symbol like this, it's hard for me to tell whether or not the I is underneath the square root or not underneath the square root. And so to avoid that kind of ambiguity, we just make sure that we put it out in front so that now we recognize that it's not inside of the square root. So now for this last one. The tendency of some people is to say, well, when I'm multiplying two radicals, what I can do is I could just multiply the insides. So I'm going to show you the wrong process first and say that this is wrong. What I am not able to do is say the square root of 9, or I'm sorry, the square root of negative 9 times negative 4. So although that's a property of radicals, that only is true when the numbers, when the radicands are positive. And the reason for this is if I take the square root, now when I multiply a negative times a negative, I get positive 36. And therefore you would think that 6 is the answer here. But again, that's wrong. Let's take a look at the correct way to do this. Instead, what we should do is evaluate each of those values separately. So we need to realize that this is the square root of negative 9 or 3i, times the square root of negative 4, which is 2i. So notice that that becomes 6i squared. So the process of working with multiplying imaginary numbers together works just like regular exponents. I times I is I squared. But we need to take a little side note here and recognize that if I is equal to the square root of negative 1, then what happens when I square I? We'll notice that the square cancels with the square root, and therefore I'm left with the fact that I squared is negative 1. So when I take an imaginary number and square it, it becomes a real number again. So I squared becomes the value negative 1. And that's still multiplied by 6. Which means that my final answer is actually negative 6 and not positive 6. So we should realize that 6 is incorrect. So when we deal with powers of numbers, we should realize that this pattern continues to emerge. We see that I is the square root of negative 1, but if I square I, it becomes negative 1. By looking at a division problem now, typically whenever we want to simplify a radical over a radical, we need to rationalize the denominator, which means get rid of the radical in the denominator. So the first thing I might recognize is that the denominator is an imaginary number, so I can start by pulling out an I. But now I'd like to multiply by something that's going to cancel the radical. So I know that multiplying the denominator by root 3 will cancel the radical here. Okay. But now I'm still left with this I in the denominator. I is still a radical, so even if I were to be left with 3i in the denominator, I'd still technically have a radical. So I got to get rid of the radical as well by multiplying by an I, keeping in mind that I squared is negative 1. So now I'm going to multiply top and bottom by 40 or by I root 3. So that simply becomes I times the square root of 48 times 3. Now I'm going to have to factor this to simplify, so I don't want to multiply those just to go backwards again. But now notice on the bottom I get I squared times 3. So if we simplify that, notice that this becomes I times the square root of, well, 48 you could think of as 16 times 3 times the extra 3 that's already there. But now notice in the denominator, I'm left with I squared times 3, which is negative 3, since I squared is negative 1. So now if we take a look at the simplification of the radicand, the square root of 16 is 4. 3 times 3 gives me 9, so the square root of 9 is times 3, times the extra I, divided by negative 3. And now we want to take a look at this and recognize that this becomes, by canceling out a 3, negative 4i. So this quantity of the square root of 48 over the square root of negative 3, just by dealing with the properties of complex numbers, simplified to become the imaginary number negative 4i. Now I'd like you to recognize as well that this is in fact in the form that it's supposed to be. Since all numbers are supposed to be in the form a plus bi, this is actually 0 minus 4i. So we know that when we have it in that form, then we've completed the problem. We can now apply operations with complex numbers, most notably subtracting, multiplying, and squaring. So let's take a look at each of these separately. So if I happen to be a variable, then I could add 3i and 2i. So even though I is not a variable, when we apply operations, we can treat it as a variable until the end of the problem. So in this first process, we could say 4 plus 3i, and recognize that if I'm subtracting this quantity, I'm going to have to distribute the negative to both, which is going to give me plus 2 minus 2i. And now you can add the real numbers, add the imaginary numbers, and my final result is 6 plus I. And sure enough, we're done because of the fact that this is a plus bi. More specifically, b is 1. So when you're adding or subtracting, you're really just adding or subtracting like terms, namely the real numbers and the imaginary numbers. So what about this next one? Now we could apply the distributive property just as if these were two binomials. So we could say 4 times 2, which is negative 8. 4 times 2i, which is 8i. If we multiply 3i times negative 2, that gives me negative 6i. And 3i times 2i is plus 6i squared. And we can combine these two terms together here in order to get negative 8 plus 2i plus 6i squared. But notice that doesn't look like a plus bi because of this I squared term. So we need to figure out what to do with that I squared to simplify this, but recognizing that I squared is negative 1, then that last term turns into a real number. So we're left with negative 8 plus 2i plus 6 times negative 1. So now if we combine the negative 8 and the negative 6, we're left with negative 14 plus 2i. Every complex number will eventually simplify to look like a plus bi, just as this one does as well. Now for this last example, what oftentimes we have a tendency to do is distribute the square. We've got to be very careful because that's not what it means to square something. What it means is to multiply it by itself. And notice that now that turns right into the type of problem that we just did in the center. Expanding gives me 16 plus 12i plus another 12i plus 9i squared. But now we should remember that I squared is negative 1. And we can combine each of these two terms. So that gives us 16 plus 24i minus 9. And so that I squared term turned back into a real number again, allowing me to combine it with 16. And therefore I'm left with 7 plus 24i. And sure enough, as every complex number is also in the form of a plus bi. Let's take a look at how to divide numbers with complex numbers or with imaginary numbers. For these two examples, you should realize that neither of these are in the form of a plus bi. This one, for instance, is a real number divided by an imaginary number. This one is a plus bi, but it's divided by another a plus bi. So neither of these numbers look like a plus bi. And so what we need to do is figure out how I can get rid of that I in the denominator, because remember, it is a radical. So if I think about 3 over I need to multiply by something that's going to eliminate that radical in the denominator. That is a radical because I know that it's the square root of negative 1. So notice we can multiply by I on top and bottom. Look at why that was beneficial. We know that what's going to happen here in the denominator is that I get I squared, which is now back to a real number again, while the numerator becomes 3i. So now because we realize that I squared is -1, then what we really have is 3i divided by -1, and therefore -3i. So we should see that 3 over I is actually the same as -3i. And now that is in the form a plus bi because it looks like 0 plus or minus 3i. And therefore it's simplified and I know that I'm done. But if we take a look at the one on the right side over here, we should realize that now we need to multiply by something that's again going to eliminate the I. So you may think again, let's multiply by I. But look at the issue with this. Although I will cancel this one because that becomes I squared and therefore a real number, now the I would just move on to the 5 to get 5i. And so I really haven't eliminated the imaginary number in the denominator, so multiplying by I isn't going to work for us. But you might remember that when you dealt with two terms in radicals, multiplying by the conjugate got rid of the radical. So let's see what happens then when I multiply by the conjugate of the denominator. We should now see that both of these are binomials, which now can be distributed. So let's take our time distributing the numerator and denominator. We get 15. 3 times 2i is 6i. 2i times 5 is 10i. And 2i times 2i is 4i squared. Now for the denominator. Notice that if I multiply 5 times 5, I get 25. 5 times 2i is plus 10i. But when I multiply -2i times 5, I get -10i. And notice how multiplying the positives and the negatives, since they're the same terms, is going to cancel out the imaginary part. So multiplying a complex number by its conjugate will cancel the imaginary number. And what's left is minus 4i squared. And so now we're ready to simplify the numerator, which becomes 15 plus 16i plus, but now remember, I squared is -1. So we need to rewrite I squared as -1. And the same thing happens on the bottom, where we have 25 minus 4 times I squared. But again, I squared is -1. So we're pretty close to being finished here, because all we've got to do now is simplify by adding 15 minus 4, which is 11. And now I get a different complex number in the numerator, 11 plus 16i. While in the denominator, I get 25 plus 4, which is 29. And although that kind of looks like my answer, it doesn't yet look like a plus bi. It looks like a plus bi divided by c, or divided by some other real number. So we just need to remember the properties of fractions, which allows me to separate fractions if I'm dividing by a single quantity, which means that my final answer is 11 over 29 plus 16 over 29i. And sure enough, I know that I'm done because of the fact that it again looks like a plus bi. So we've learned a really important property of complex numbers. That property says that if I multiply a plus bi times its conjugate, then that's going to give me a squared plus abi minus abi, abi minus abi. And finally, bi times bi is b squared I squared. We could see that abi cancels with abi, and I squared becomes -1. And so when I multiply complex conjugates, my answer becomes a squared plus b squared. And so it turns out that multiplying complex numbers turns back into a real number. This number is real because it doesn't have any imaginary part. And so this is actually a pretty helpful tool, because what we're able to do now, for example, is to factor a sum of two squares. Before, this was unfactorable if you think back to algebra. There was nothing that I could turn this into over the real numbers, because x times x would be x squared. But notice that if I notice that 16 is, say, 4 times 4, in order to get a positive result, I know that I'm going to have a positive and a positive, but that would cause me to get an x term in the middle. So I know that that's not it. So then I think, well, in order to get a negative or a positive 16, I need -4 times -4. But that wouldn't work either, because that would give me a -4x minus 4x, or -8x in the middle. So in algebra, we just said we weren't able to factor this, but now we can, because we know that if I have a squared plus b squared, that does factor into a plus bi times a minus bi. So what that means is that this actually factors into x plus 4i and x minus 4i. So that's an interesting consequence of this, this process of multiplying a complex number by its conjugate. Okay. Now I'd like to take a look at one of the most intriguing results from complex numbers. And that's what happens when we start to raise I to various powers. So let's take a look at I and I squared, and I to the third, and I to the fourth. And let's just start with those and think about how I can simplify each of these. Now I know, based on the fact that all complex numbers should simplify to a plus bi, that complex numbers should never have a 5i to the 7th term, because that doesn't show up in the form of a plus bi. So that must mean that 5i to the 7th will simplify to either a real number or an imaginary number. So every single number must look like a plus bi, and therefore, let's begin. Now we already know that I to the first power, well, that's obvious, that's just I. So now we see that I to the first is equal to I. And we also took care of I squared. We should realize that I squared is I times I. But if you remember what that showed, that was essentially just the square root of -1 squared. So we know, and we've already proved, that that becomes -1. So just for the first two here, we can see that I to the first power is imaginary, while I to the second power is real. So let's continue with I to the third. Why don't we rewrite I to the third in terms of I squared and I, since I already know what those are? So I know I to the third is I squared times I, so I could rewrite that as -1 times I, which means that I cubed is negative I. So now I to the third power is simplified again to a basic imaginary number. So now let's look at I to the fourth. I to the fourth is I squared times I squared. But the reason that's helpful is because that's just -1 times -1. So I to the fourth is exactly the same as the real number 1. So this is some pretty intriguing results that are already starting here. Turns out that I to the first power is imaginary, but I to the second power is real. I to the third power is imaginary, but I to the fourth power is real. But now let's go ahead and see what happens if I continue. Let's raise this to the fifth power, and then to the sixth power, and to the seventh, and to the eighth. Okay, well, since I know that I to the fourth is automatically just equal to 1, these can all be really helpful to say I to the fourth times I. That's the same as I to the fifth. I add the exponents. But notice that I to the fourth is already known to be I, or is known to be 1. So this is really just 1 times I, which is I. So I see that I to the fifth is actually the exact same thing as I. But notice that that's exactly what showed up back here as well. So let's take a look at I to the sixth. I to the sixth power is also the same as I to the fourth times I to the second. But we know from the previous column that I to the fourth is 1, and I to the second is -1. So 1 times -1 is -1. So now that shows us that I to the sixth is -1. So raising I to the sixth power is a real number again. So we should already start to see then that every time we raise I to an odd power, like 1 or 3 or 5, I get imaginary numbers. But every time I raise I to an even power, like 2 or 4 or 6, I get a real number. And that's because the I values are canceling out. And so let's take a look at how to simplify I to the seventh. I to the seventh is I to the fourth times I to the third. But notice why I keep using I to the fourth. I to the fourth is already 1. And 1 times anything is itself. So that means that if I cubed is -I, that I to the seventh is the same thing as -I. We should see again that I to the seventh is now -I. And if you haven't noticed yet, we should realize that this pattern is continuing. I, -1, -I, 1. I, -1, -I. And if this pattern is continuing, then my guess is that this value down here is going to equal 1. But let's see if that works out, because I to the eighth is I to the fourth times I to the fourth, which is simply 1 times 1. And therefore, sure enough, I to the eighth power is equal to 1. And so this is actually very intriguing, because that implies that every time you get to a multiple of, or a power that's a multiple of 4, your answer will be back to 1. So the pattern for the powers of I is that it will always be I to the first is I, then -1, then -I, and then 1. And more importantly, we should also realize that I to the fourth will give the same value as I to the eighth, which will give the same value as I to the 20th, or I to the 44th, or I to the 4,000th, every single one of these are giving me the same result of 1. Which is why if I wanted to simplify, for example, a power of I, for instance, maybe we could simplify a couple of these. Let's say we want to simplify I to the 15th and I to the 82nd. Well, all we have to think about here is the closest power of 4 that's near 15. So I could realize that I to the 15th is the same as I to the 12th times I to the 3rd. This is helpful because I know that I to the 12th, since 12 is a power of 4, is automatically equal to 1. And now I'm multiplying that by what I know I cubed is. But based on our pattern, I cubed, being an odd number, is negative I. And therefore, I to the 15th is exactly the same as negative I. So it's not necessary to list out every power just to be able to simplify a power of I. Let's do this one. We realize that 82 is not a multiple of 4. We realize that 81 is not a multiple of 4 either. But 80 is a multiple of 4. So I can rewrite this as I to the 80th times I to the 2nd power. And since I know that I to the 80th is 1, because 80 is a multiple of 4, I now know that this is 1 times the value of I squared. But we also know that I squared is negative 1. And therefore, this tells us that I to the 82nd power can be simplified to the real number of negative 1. And so going back to our pattern in this real or imaginary result, I should realize that every one of these does in fact look like A plus BI. I can think of this as 0 plus I, and this as negative 1 plus 0I. This is 0 minus I, and this is 1 plus 0I. Every one of these now looks like A plus BI, even though each of the powers separately needed to be simplified before it looked like that result. So now we have methods of being able to simplify all complex numbers to this form of A plus BI simply by adding, subtracting, multiplying, or dividing those quantities.